Welcome to video 3 of the AquaGate security series. In this video we cover the final 3 vulnerabilities: V5, missing authorization on admin routes; V6, the Werkzeug Debug Mode exposure; and V7, missing input validation and a race condition. We finish with the defense in-depth fixes for all 7. Here's where we stand. Videos 1 and 2 covered the attack surface. XSS stole session cookies, session fixation and missing cookie flags let us replay those cookies, and command injection gave us a root shell inside the container. Video 3 tackles the server-side controls, or rather the lack of them. Anyone can reach admin routes, the Werkzeug debugger exposes source code in a Python console, and the passage request form accepts garbage data with no protection against duplicate bookings. V5, missing authorization. There's an important distinction here. Authentication answers "Who are you?", while authorization answers "What are you allowed to do?" AquaGate checks neither on its most sensitive routes. Both /admin and /diagnostics are completely open. Any HTTP client, authenticated or not, can reach them. Here's the code. On the left, the insecure admin route. No decorator, no session check, nothing. Any GET request to /admin returns the full admin panel. On the right, the secure version adds an admin-required decorator. If you're not logged in, you get redirected to the login page. If you're logged in but not an admin, you get a 403 forbidden. One decorator prevents both cases. Let's demonstrate V5. We'll navigate directly to /admin with no session cookie. On the insecure version, it loads the full panel. Then we'll try the same URL on the secure version and get redirected to login. We can also log in as an operator on the secure version and try /admin. That gets a 403. Here's the insecure admin panel loaded without any login, just navigating directly to /admin. All passage requests, lock data, and user information are fully visible to anyone. Here's the side-by-side result. On the left, insecure /admin with no cookies, HTTP 200, full admin panel with all passage requests and lock data. On the right, secure /admin with no cookies, HTTP 302, immediately redirected to the login page, no data exposed. V6, debug mode exposed. Flask's debug equals true is meant for development. It activates the Werkzeug interactive debugger, which catches any unhandled Python exception and renders a full stack trace with source code snippets and local variable values in the browser. There's even a terminal icon on each frame that opens an interactive Python console. In production, this is an open door to arbitrary code execution for any visitor. 2 flaws combine here. V1 let us inject template syntax through the search route's render template string call. If we send /search with q equals double brace 1 divided by 0 double brace, Jinja2 evaluates that expression, raises a 0 division error, and debug equals true catches it. The Werkzeug debugger opens. The secure fix addresses both. Use render template instead of render template string, and set debug equals false with a custom error handler that logs the exception server-side but shows nothing to the browser. Let's trigger it. On the insecure version, we navigate to /search with q equals curly brace 1 divided by 0 curly brace. On the secure version, the same URL returns a clean error page with no stack trace. And here's the Werkzeug debugger triggered by the SSTI payload. The full Python stack trace is visible in the browser, with source code snippets at each frame and an interactive console available to any visitor. Here's the result. On the left, the Werkzeug interactive debugger showing a full Python stack trace, the source code at each frame, and local variable values, including the query string we injected. On the right, the secure version shows a clean error page with a generic message. The exception is still logged server-side. Operations can investigate it, but nothing leaks to the browser. V7, no input validation plus a race condition. 2 separate weaknesses in the passage request flow. First, form data is stored exactly as submitted. No type checking, no range limits, no length caps. Submitting a draft value of ABC or a vessel name 10,000 characters long gets silently stored. Second, the database has no unique constraint on the ETA and lock ID combination, so 2 simultaneous requests for the same time slot both succeed. Here's the code. On the left, the insecure version pulls all 5 form fields as raw strings and inserts them directly. The schema stores length and draft as text, so anything goes. On the right, the secure version validates every field. Vessel name required and capped at 100 characters, length and draft parsed as floats with range checks, ETA validated as a datetime, lock ID checked against the known set. If any check fails, a 400 is returned and nothing is inserted. The unique constraint on ETA and lock ID catches any race condition that slips through. Let's test the input validation. On the insecure version, we submit garbage data, a 10,000 character vessel name and ABC for draft, and it gets stored without any error. On the secure version, the same submission returns 5 validation errors and nothing is written to the database. Here's the secure validation in action. Server-side validation collects all errors in a single pass before rejecting. No partial inserts. 5 checks. Vessel name required and under 100 characters. Length as a number between 0.1 and 500 meters. Draft the same, ETA as a valid datetime. And lock ID from the known set. HTTP 400 returned. No redirect, no insert. Now the race condition. We'll send 2 concurrent post requests for the same time slot and same lock, using curls ampersand to launch them in parallel and wait for both to finish. On the insecure version, both return HTTP 302, 2 bookings created for the same slot. On the secure version, one succeeds and the other gets a 409 with that time slot is unavailable. The race condition side by side. On the left, the insecure admin panel shows ship A and ship B both booked for the same ETA at the same lock, 2 conflicting entries in the database. On the right, the secure dashboard shows the 409 error. That time slot is unavailable for the selected lock. The unique constraint did its job. Defense in depth for v4 and v5. For command injection, the most important fix is dropping shell equals true and passing subprocess a list. The shell never sees the input, so semicolons are just characters. In the secure version, we went further and removed the subprocess ping entirely, replacing /diagnostics with internal health checks. For missing authorization, the admin required decorator pattern is clean, one definition applied everywhere. Forgetting, it becomes a visible code review gap rather than a silent production bug. Fixes for v6 and v7. For debug mode, debug equals false in production, full stop. Errors are still logged server-side with the full stack trace. Your ops team can investigate, but the browser gets a generic message. For input validation, 2 layers working together. The application validates every field before touching the database, and the schema enforces types and the unique constraint as a safety net, so even if a bug in the validation code lets bad data through, the database rejects duplicate bookings. Video 4 will walk through the secure version side by side with everything we've done. Every attack from videos 1 through 3 gets repeated and blocked. The XSS payload renders as escape text. Cookies show HTTP only and same site strict. /admin without login gets a 302. An operator trying /admin gets a 403. The SSTI injection gets a clean 500 page. The race condition gets a 409, and /diagnostics no longer runs any subprocess at all. That's all 7 vulnerabilities. V1 through V4 from videos 1 and 2, and V5 through V7 from this video. Client-side injection, session management, cookie hygiene, command injection, access control, error disclosure, and input validation, all exploited on the insecure version, all fixed in the secure version. Video 4 confirms every fix holds under the same attack conditions.